Hi, everybody. Welcome to Astronomy on Tap Groningen. I'm Nika Jurlin, and I will co-host today's event. So first off, we start with Dr. Leonard Burtscher. He is an astronomer from Germany, and he finished his PhD and also his postdoc in Germany, studying mostly active galactic nuclei. Today, Leo will talk about astronomical climate lies.
All right. I suppose people can see and hear me, at least I hope. So, hello. Let me now start sharing my entire screen. And I'll move to my presentation. Okay, so this talk is titled Astronomical Climate Lies, and it came essentially as a, as always, or as often, a talk that I just wanted to do because I wanted to know how many astronomical factors are actually involved in the changing climate that we see. Of course, I know the answer, and I hope all of you know as well, that astronomical factors are not the reason for the climate crisis that we have. But nevertheless, it's actually quite interesting from an astronomical and climate point of view to study what factors there are. So in this talk, I'll cover first a little bit about the habitable zones that you may have heard in the context perhaps of exoplanets. This is kind of a broad introduction of what is our cosmic environment and what does it mean for complex life. And then we go to two main factors that have a big influence actually on the Earth's climate, although, and I will repeat this many times, not on the climate crisis. And that's our solar system, or the sun, more specifically. So what influence the solar radiation has on our climate. And then our orbit around the sun. So that's the Earth orbital parameters. And then I'll end with a little summary of what relation there is to the climate crisis. All right, so let's start with some real astronomy. So there are places in the universe where complex life can develop, and others, most places actually, where this is probably not possible. The exact details of all of this, of course, are still very much unknown. There is, since only really a few years, this study of astrobiology has taken off quite a lot, of course, with the discovery of exoplanets, which received the Nobel Prize just 2 years ago or so. Now we know something like 4,000 exoplanets, but we know none yet that are really that host life. We know a couple that might host life, but none that really do, except our own, of course, which is not an exoplanet strictly. So we can ask for what factors are probably involved in making a place suitable for complex life. And the term complex life really comes from a book that I can quite recommend to read, which is called Rare Earth. And that book essentially tells the story of why Earth is so special and why it's quite likely that we are the only ones who are, we are the only complex life in our galaxy, because there are so many factors that need to get together. And the authors argue that simple life, like, I don't know, some microbe or so, might exist in many places, but complex life, which means, as we know, an evolution that lasts over really many, many millions of years until something like us exists, requires not just favorable conditions for life in a short amount of time, but stable favorable conditions over many, many million years. And for that, our Milky Way is actually, and especially our solar system, is actually quite special. So our galaxy, the galaxy in which we live, first of all, is a galaxy with little nuclear activity. So the black hole that you probably know about in the center of our Milky Way, about 4 million solar masses, heavy, is not very active. I mean, from time to time, it swallows something like a couple of comets, or some larger pieces that are perhaps a few Earth masses large, but nothing really substantial. So it doesn't produce giant jets or huge energy outbreaks like is seen in a few other galaxies, at least currently not. That might have been different many years ago, 6 million years ago, for example. There might have been an outbreak, but that didn't reach us. And that's the second point here, because our location is relatively far away from the central region where energetic phenomena happen also besides from the from the black hole, just because you have a lot of stars. But it's also not too far away, so we have enough material still so that planets can actually exist. And then finally, we live in a relatively quiet neighborhood, the so-called local bubble, where several supernovae went off a long time ago. And so now not much is happening there. It's actually an underdense region where the sun is living in the center and the surrounding of some parsecs. And so that might also be favorable for life. And then the next habitable zone that there is the habitable zone around the star. And so this is a picture that I took from the ESO webpage when another exoplanet just had been discovered, in this case Gliese 518. But this is mostly actually to illustrate our solar system. So you can see the inner 4 rocky planets and Jupiter here, and the sun, and you can see this band here, this light band, which indicates at what distance from the sun essentially liquid water exists on the surface. And this is known as the habitable zone, and we are of course in that. You can see that we're perhaps a bit closer to the hot end, so to say, than to the cold end, but still we're quite nicely in there. And there's a couple of other factors that make our solar system, our sun, very favorable for life. So our sun is relatively quiet. There has actually just been research a few weeks ago that said that compared our sun with similar stars, so-called solar type stars in our neighborhood, and they found that our sun was really extraordinarily boring, let's say. So it doesn't do a lot, which is good for life. So it doesn't have major outbreaks, magnetic activity and stuff. It has it a little bit, of course, but by far not as much as other stars. And there are further factors, which I think I won't go into here, but we can discuss this later, like the moon, which stabilizes the Earth orbit, and Jupiter, which keeps away asteroids. So a number of factors that make this quite nice. All right, okay, so this is the big picture of the environment in which we live. And these are, of course, all factors that are essentially stable for, timescales of thousands of years, except 2, and that's the solar activity and the Earth orbit. And those are the ones I want to discuss now more. So you might know that the sun has an activity cycle of 11 years, or very exactly, actually 22 years, but that's just because the magnetic field rotates. It's once here, and then it rotates this way, and then here, and you can see this as the 11-year cycle, and then it rotates further, but the second 11-year cycle is more or less has the same phenomena as the first cycle. And so this is these are some pictures of the sun, where you can see the range of activities that is typically observed from a very active sun, let's say in the lower left, and then it goes to a less active sun, and then it becomes more active again. And so at the moment, actually, we're, you can see in this graph here in 2020, we're really at the minimum of a solar cycle between so-called cycles 24 and 25. And not a lot is happening. So if you went out with proper solar protecting filters, of course, and observed the sun, you would likely not see an image like in the lower right with a lot of sunspots, as you can see here, but you would likely see a solar disk, yellow or whatever your filter gives you, with probably not a lot happening out there. But this wasn't always the case. So the sun is sometimes more active, and there's also longer term cycles in the sun. And one of these cycles actually led to one of these cycles is connected, I should say, to a cold period, at least in Europe. And this cold period has been described by many people, but most nicely, I think, depicted here on this picture by Hendrik Averkamp, which you can see in the Rijksmuseum. Well, not at the moment, of course, because it's also closed, but you can see it online also, Rijksmuseum.nl. It's called Winterlandschap met ijsvermaak, so winter landscape with happy time on the ice. And at this time, 1608, it was actually unusually cold in Europe. As you might also know, this is actually 1 year before Galileo pointed his telescope to the stars for the first time. So you can ask now, okay, how do we know what the solar activity was at that time? And with this, I'd like to introduce you to so-called proxies, which is a difficult topic that is also not my specialty, of course, but it's in this case actually quite easy to understand. So this is the solar activity that has been reconstructed for the last more than 1,000 years based on measurements of carbon-14. So you might know that carbon, one of the most frequent elements in the Earth crust, comes with two natural so-called isotopes. So one has 12 atoms, that's the normal carbon. One has 13 atoms. And then there is a radioactive version of it called C14 that has 2 extra neutrons compared to the normal carbon. And it decays in about 6,000 years into nitrogen. And you can measure it, and this radioactive carbon is produced by cosmic rays that come mostly from the sun. So you can then deduce that the presence of this atom, or the deviation of the number of these atoms compared to the long-term average, depends on the cosmic rays that hit the Earth, and that again is an indicator for solar activity. Now, how exactly that is produced and calibrated, I actually have a second slide on that, but we can do this in the discussion in case you really want to know. But let's just look at this plot here. So you can see here the deviation of this specific carbon atom. So let's call this now just the solar activity as a function of time. And you can see that between, let's say, 1400 and 1800 or so, there was kind of a little dip in the solar activity. And this indeed coincides with what is known as the Little Ice Age. So this is roughly when Hendrik Averkamp made his picture in 1608. And that actually led to a lot of speculation that this reduced activity of the sun might be connected with the so-called Little Ice Age. This is by far not proven. I mean, it's an interesting possibility, but there are other effects as well that might play a role. One is orbital cycles that we discuss in just a few minutes. Another one is volcanic activity. So it is known that if a lot of volcanoes erupt, they produce lots of dust, and this dust increases the albedo of the Earth. So it deflects more sunlight, and it leads to less heating of the Earth essentially, and that produces more ice, and then you have actually a feedback cycle that goes into an ice age. All right, so is it then the sun's fault that our climate is heating up now? Well, this question can be very clearly answered with a no, and it is studied in quite some detail. There has been many years ago various people who claimed that it was the sun. They often then like to show this graph only until about 1960, where it almost looks like a correlation. But if you look at the more recent time, then you can clearly see that there is this temperature deviation starting in the 1970s very clearly, and has reached now something like 1 degree above the so-called pre-industrial time. And you can see the solar activity, which is actually measured based on the sunspots since for the last 100 years, or more than several hundred years actually, or from these proxies. And you can see that there is no correlation between these two. So the sun is not the culprit. Fortunately, unfortunately, well, we can discuss this, but at least it's not the sun that's causing this deviation in temperature. Now, if we go a little bit further back in time, we can look at the temperature variations over the last thousands of years. And this is done with another so-called proxy, so another measurement that you can easily get, or that you can get over this long time scale. In this case, it's the deviation of, again, a specific isotope, so a specific variant, let's say, of the atom oxygen. And there's one called oxygen 18. It's a little bit heavier than the normal oxygen, so it's more likely to be in ice than in the air. And indeed, this isotope is then used as an indication for temperature, actually, because if more of this is found in the ice cores, then that means there is more a higher fraction of water that is bound in ice. And if you look back here and then you look at, okay, how many cycles do I have and how often do these cycles appear, you see that it's roughly every 100,000 years, so 0.01, 1 in 100 cycles per 1,000 years, so 100,000 year is roughly the cycle that we see. And indeed, over the last several million years, every 100,000 years we had an ice age. And that's at least interesting to say, oh, why is that actually? And there's a number of reasons why that could be. And a Serbian geologist, astronomer, discovered them for the first time. We mentioned him just later, Milotan Milankovic. And I'll just point out 4 possible effects. So one is called orbital eccentricity. That just means that the sun isn't, or the Earth isn't exactly circulating around the sun in a circle, but it has an ellipse. And the eccentricity of this ellipse is changing over time a little bit. Another one is the tilt, the 23.5 degree that we have now, that changes also over time. That's the one that produces summer and winter. It is variable with time. Another one is the precession of the apsides. Sounds very difficult, but you can see here in the image what it does. So the point closest to the sun is, so if you take this fixed, then the ellipse of the Earth orbit is rotating around the sun. And the last one, this is a complicated picture, but it's actually still easy to understand, is the inclination of the orbit. So if you think of a reference plane, which is essentially all other planets, or mostly Jupiter actually, who is the most massive, the one with the most angular momentum. You take that one and you look at the Earth orbit. This is the greenish plane here. Then there's an inclination between these two, and this inclination changes with time. And then if you look at which of these factors has this 100,000 year cycle, the one that wins is actually the inclination. And this is relatively recent research. So this has, for a long time, there have been discussions over what really is the dominant effect here. But it seems it's inclination that causes this shift every 100,000 years. And as I said, this has been described already more than 100 years ago, actually during the First World War, by Milutin Milankovic, who studied this. He didn't know at the time that it was inclination, but he named the number of effects that could be it. And the possible reason is also interesting. So in this paper that is cited here on the side, they say that this might have to do with the Earth orbit meteoroid shower that you have in the summer, for example, the Perseids or so, but then in a massive way, where you have so many of these meteoroids or comets that hit the Earth's atmosphere, that you really get again this cycle like in volcanoes, that you have more extinction, and then you have more ice, and then you have even more albedo due to the ice, and then it gets really cold. All right, so that brings me close to the end, or at least to the last point, namely to the question, what is then the climate crisis, and is there any relation? I already took it away, but I think it's still interesting to see this drastic difference in effects. So the changes we looked at were hundreds of thousands of years. The axis that you can see here, you can see the ice ages, and this is in this plot just the CO2 concentration, which also changes during the ice age cycles. That's a different topic. But you can see here that the change that we have observed in the last 50, 100 years or so is really dramatic, and it has reached levels that are far, far higher than anything that we have seen over the last hundreds of thousands of years. And a very nice depiction of this effect is actually done in this comic that I can highly recommend to read in full. I just have a few snippets here, and you see the link in the bottom. So this is by Randall Munro, the maker of XKCD, a really nice physics comics, but these are comics that are really meant to explain physics for everyone. So then this is really very nice to read. And he has this huge comic that you can see the scale here. It starts at 20,000 years before our time, and it goes in 500-year blocks down. And you can see the dotted line here is the temperature on Earth. And indeed, 20,000 years ago, it was a bit colder, and then it rised, and then we have the so-called medieval warm time, and then it stayed very, very, very constant over a long time. And then now we suddenly have this increase here, that this is 2016. It has, of course, continued in the last 4 years. That is really unprecedented over the last really many 10,000, 100,000 of years. Actually never seen before that there is such a really fast increase. Of course, you can also have this in a little more scientific way. This is the kind of the summary of what we know about the Earth's climate over the last 100 years or so. You can see in different colors and in black, actually in black, red, and green, the observed temperature curves for the global mean temperature, which is a difficult thing actually to estimate. So there's different projects that do this, and you can see that that these different estimates actually agree very well with each other. And you can also see this clear deviation since 50 years or so, that you have this increase in temperature. So this is now in degree Fahrenheit, so that's why it's more than 1 degree, in case you wonder. And you can see in blue, in thick blue, what they call here natural forcing. So this is everything that you expect from external factors, and that includes these astronomical factors like orbital changes and solar radiation. And you can see that these have a very, very minor effect, and actually in some cases even a negative effect. So they can before not explain what we are seeing. Yeah, and this is really close to the end then. So then the question is, can astronomy do something to solve the climate crisis? And this is going to be answered in the second talk by Michele just afterwards. So stay tuned. If the astronomical factors have nothing to do with the climate, can astronomy still do something? We will see. Okay, so this is my summary with 3 take-home points. The astronomical environment determines much about the habitability. So we know that in many places, like in this beautiful galaxy that you can see here in the backdrop, Centaurus A, it's probably not a nice place to live, because we have in some galaxies massive outbursts of radiation, particles bombarding planets, or just lots of stars exploding. So the atmosphere, the astronomical environment has a big impact on how livable a planet is. But the timescales that we observe in the climate crisis are on a very different scale. So this is really hundreds of years, whereas astronomical scales are more likely tens of thousands or millions of years. Yeah, and then this is really the conclusion that I want to convey here, that all these other factors are, I think, quite interesting to study, what might have caused the ice ages, but it is not a reason for what we see right now. So the climate crisis that we have is really our climate crisis, and we need to solve it ourselves. Thank you.